All right, today we are going to talk about, we're going to get complex today. It's going to be unreal. Those are great. Those are great jokes when you're all by yourself in your office. No one here to laugh with you. Anyway, the complex numbers. So mathematicians, not just mathematicians, but we have two kind of number systems. Not really two, but the complex numbers are going to include numbers that maybe aren't the normal kind of numbers that we are used to seeing. So for example, something like x squared plus 1 equals 0. We know what the graph of that looks like, right? That's a parabola shifted up 1. And if we talked about the x-intercepts of this function, we see that there are no real numbered solutions because the Cartesian coordinate system, right, is basically two axes that are just made up of a real number line, right? The x-axis is a real number line that runs horizontally. The y-axis is a real number line that runs vertically. But that doesn't mean that we can't talk about solutions of something like this equation right here. I mean, let's open our minds and let's not just try and think about solutions in the real numbers. It really is useful for us to think about solutions to things like this. Whoa. X squared equals -1. And I don't want you to think that complex numbers, or this is going to sound weird, imaginary numbers don't exist. And I kind of hate that we call them imaginary numbers almost because they're not like our real numbers, but that doesn't mean that they don't exist. We use imaginary numbers when I teach differential equations and we look at the oscillation of a spring. Let's say we can describe the oscillation of that spring, or if we attach a weight to a spring and look at what happens when we pull that weight back and let it go and let it oscillate, we can describe that movement using some equations that involve complex numbers, that involve that involve that imaginary number. So these numbers exist. We just are defining them differently than how we define real numbers, okay? So here, this x squared equals -1. If I square root both sides, we get this thing, we get the square root of -1. And in the real numbers, okay, in the real numbers, this guy does not exist. Does not exist in the real numbers. I cannot plot this on my Cartesian coordinate system. So what we want to do is we want to expand our viewpoint now. We want to talk about this number, this actually being a number, and it is going to be a number that exists in kind of our new system, and that's going to be called the complex numbers. So before we get to what a complex number is, we're actually going to define a number that actually is equal to the square root of number 1. So the number I, and notice it is a number. It's just not those real numbers. That's okay. Like, we can think about things differently. That's the great thing about mathematics, is it helps us define new ideas and it puts logic to those ideas, and it helps us see that there are other things out there besides maybe just what we've been taught since, second grade. So the number I is defined such that we are going to define I to be the square root of -1. And if we square both sides of this equation, then we get the other result too, that I squared is -1. And so this is going to allow us to take square roots of negatives. We're not going to be in the real numbers, but that's okay. We're going to take square roots of negatives, and we're going to be in something called the complex numbers, or the imaginary numbers. But again, don't think of imaginary in terms of how we think of it in everyday life. A unicorn is imaginary. They do not exist. Imaginary numbers do exist. Okay. I know. It's a little bit crazy. So let's look at some examples, the square root of -1. So let's express each number in terms of I. All right. Sorry, there are people outside my office talking, so I don't know what they're talking about, but you might get to hear a fun story in the background. All right, so the first thing, let's look at something like the square root of -4. So this might be like the solutions to something, an equation like x squared plus 4 equals 0. So the way we're going to describe this in terms of I is I'm going to see if I can, I'm going to rewrite this because I know I is the square root of -1, I want to rewrite this so that I have a -1 in there. And I'm going to break up the square root over multiplication. That's okay. Your math teachers are not going to freak out if you do that, because it's okay to break up square roots over multiplication. Not okay to do it with addition and subtraction, people. Don't you dare. Okay, so what is this? The square root of -1 is an I. What's the square root of 4? That's 2. So I have I times 2. And just like, remember, I is not a variable. I is a number. However, we usually write that as 2i. Just like if I had an x in there, we would usually write that as 2x. Okay, and that's as simple as that. That's how we will simplify things like that. What if we had, like the square root of -7? Here, same idea, and you'll get to where you don't have to do these steps every single time. This would be the square root of -1 times the square root of 7. And actually, a lot of you have probably already seen this. Square root of 7, I can't really simplify at all. So I have I root 7, or I could write root 7i. Just be really careful there that I is not included underneath the square root there, or the radical, okay? So these are some examples of how we can simplify. A lot of times when I do these, I just think of that negative just becomes my I, basically. So I'm just going to, I'm going to skip this step a little bit, and I'm going to say, okay, if I pull that negative out, that becomes an I, and then I have the square root of 48. We don't want to leave it like that, though, so I have I times 48 has some factors, I believe, that are perfect squares. Ooh. Although I am doing arithmetic here by myself, which is not always a good thing. Square root of 16 is 4. Square root of 3 just has to hang out. Poor square root of 3 all by itself, because square root of 3, you're irrational. Not only are we complex today, we're also getting irrational. Let's just do one more really quick. What if I had a negative of the square root of a -49, let's say? This negative just hangs out. There's nothing really special about that negative. Oh, poor negative. I think you're special. It's okay. I shouldn't have said that. Now I feel bad. All right, what is this becoming? That becomes I, so I just get a negative I. Square root of 49 is 7. So the way I would write this is a -7. You guys have probably seen some of this before. But it's a good time. It's a good time because look at this. Now you live in a world where we don't just have real numbers. We have non-real numbers. We have complex numbers. It's good. It's good. It's good. All right. So let's talk about, so that's kind of how we're going to write things with the I, and then that's going to lead us to something kind of bigger, which is a group of numbers that we're going to call the complex numbers. And we're going to actually see that real numbers are part of complex numbers. The complex numbers just are going to include all of the real numbers and the non-real numbers. So a complex number a complex number is a number of the form. So there's going to be two parts to these numbers. So this is a number of the form, and this is just a definition, right? We are just defining a new set of numbers, a number of the form, and the way we write this form is a plus bi, okay? Where a and b are real numbers. So I'm going to do a little bit of shorthand here. I'm going to say a and b, and then this little backwards e are elements of, and you've probably seen the real numbers described as a bold R. So all this is saying a little bit of math notation so you can be, cool among your friends. I know what's cool, and that's writing shorthand math. Where a and b, again, this is our elements of, and then the bold R, which is bold in a book or something, but because I'm writing this, we use that double R, okay? Complex numbers, what's the shorthand for a complex number? I don't know what I'm doing here, people. Does that worry you a little bit? Probably should. Is a C with a line through it, a bold C. That indicates the set of complex numbers, okay? A is considered to be the real part of the complex number. Okay, that's the real part of the complex number, and B is said to be the imaginary part. So again, I don't want you to think of imaginary as it does not exist. It's just the part that represents the part of your number that's not in the real numbers, not in the Cartesian coordinate system or anything like that. Okay, so couple notes here. If b is equal to 0, right, then a plus bi, right, is going to equal a, and that means we have a real number. So do you see how all real numbers are complex numbers? Okay, so if my imaginary part is 0, then we just say we have a real number. Okay, another thing, if we have anything where the b is not equal to 0, right, then I just have the a plus bi, and we say that that's an imaginary number because it does have an imaginary part to it. Okay, so this is an imaginary number. If that b is not 0, right, so like 7 plus 2i is an imaginary number. Negative 4i is an imaginary number. Negative 1 minus 72i is an imaginary number because it has an imaginary part. And the last thing, if a is equal to 0, then we just say, then we know that a plus bi is just equal to bi, and we just say that this is a pure imaginary number, okay, meaning there's no real part to it. I know what I am saying sounds silly. I get that. It's pure imaginary. There's no real part to it, but this is an actual number. I get it. But it's just, you have to take those things in English, right, that we have meaning to, like real and non-real, and you just have to basically like think we're talking about like apples and oranges, just different types of numbers. That's all it is. Don't put any context on to being real or non-real. They're just different parts. They're just different numbers. I don't know if that sounds a little crazy. You know, when I say it out loud, I sound a little crazy, but you know, I'm used to that. It's okay because I'm a math teacher, and math teachers are all a little bit crazy. Much love to all my math teachers. But all right, so if we look at kind of how we classify numbers, you know, we have the complex numbers. This is just for fun. And I know you're like, but Sarah, this has all been fun, so this part should be more fun. Yes, it should. Complex numbers, if we look at the complex numbers, we can break those up into two groups. We can break them up into the real numbers. So complex numbers are made up of real numbers. And remember, the real numbers are where b is equal to 0, right? In my a plus bi, right? Complex numbers are a plus bi. And then I have the imaginary numbers or the non-real numbers. I don't know why my pen's been doing that. And that's where b is not equal to 0. So that's the complex numbers, just include everything. So you've been hanging out most of your life over here in the real numbers, not even knowing that you're actually part of this bigger number system called the complex numbers. And then we have, under the imaginary numbers, we have just, you know, your regular old imaginary numbers, right? And then you have pure imaginary, where there's no real part to it. So that means a is equal to 0. So that's kind of how, that's really the only way that we really group the imaginary numbers. Real numbers, you know, we can group these guys like crazy, right? I can go irrational, you know, like pi or e, and then I can go to rational, right? And then like in the rationals, I can group that. I mean, I can break this one up even more into like integers and whole numbers and natural numbers and stuff like that. But that's kind of the idea of what we have when we're talking about this new number system. So in elementary school, when you first learn numbers, I have 2 daughters in elementary school right now, and we're dealing with how to add and subtract numbers, right? And they're hanging out in the real numbers, right? And part of me wants to explain what imaginary numbers are to them, whoops, right now, but I feel like their teachers might get mad at me if I confuse them like that. So I'm trying not to do that. So what we want to do is we want to know, okay, how do I add and subtract? I have a new number system. So how am I going to deal with these when it comes to arithmetic? And the good news is addition and subtraction is exactly what, like, feels like it should do. Like when we add and subtract real or imaginary numbers, we basically combine the imaginary part and combine the real part, kind of like combining like terms when we're dealing with variables. So I'm just going to do some examples for you because these are pretty easy. And I'm only going to do like 2 examples because again, it's easy. So here's an imaginary number. It's a complex number, right? And I'm going to add another complex number. And I know it can be kind of weird that our number has 2 parts and I'm just calling it a number. It's not 2 different numbers. It's just a number. And if I were to add this number plus this number, right, I'm just going to add my real part. This kind of makes sense. -1 plus 4, right? What would that give me? That would give me 3. And then I'm going to add my imaginary part. So I have 3i minus 7i. This is going to do exactly what you think it should do. I get a -4i. Okay, pretty simple. What if I were to subtract these 2 numbers? Well, subtraction, you just have to make sure that you take the negative through. So this will take us one more step, but we're not scared. Why would you be scared? It's not scary. My daughter used to say that when she was little. It's not scary. So sometimes I say that and I sound like an idiot if you don't know the context behind it. I'm going to take the negative through to each term, obviously. And now again, I'm going to put together my real parts. So that would be a -5. And then I'm going to put together my imaginary parts, which is going to be 10. So look at this, is pretty cool. Later on, if you go higher in your math career, we're going to see like this is neat that we have a complex. If we need, anytime we add or subtract 2 complex numbers, we stay in the complex numbers. I mean, that's really the only number system we have. So we would hope that that would be true. So let's look at multiplication. Again, I'm just going to do a bunch of examples here for you. I'm not really writing down any rules. I'm just going to do a bunch of examples. So here's an example of something that this can be pretty tricky. So like if I had, let's say the square root of -10. Actually, I want to do something a little bit different here. Let's say the square root of -4, excuse me, times the square root of -25. Okay. You might want to combine these 2. So I'm going to show you the wrong way. This is the wrong way in the purple. You might be tempted to take -4 times -25 and say -4 times -25 is a positive 100 and the square root of 100 is 10. However, the problem with that is that that's wrong. So we have to be careful when we're multiplying these numbers because I can't assume things. We know what assuming does. The minute I bring these 2 together underneath the square root like this, we're assuming that we're using the same properties of real numbers, and technically we're not, because this guy right here is an imaginary number and this guy right here is an imaginary number. So I can't just bring them together underneath the square root and assume that things are going to react the same way, right? Because once I bring them under a square root, what you've done is you've kind of taken them out of the imaginary world and put them into the real world. All right. So what we need to do is we need to simplify these first using I. So the square root of -4 we found is 2i, right? The square root of -25, well, the square root of 25 is 5. And then what does that negative become? It becomes I. So look at what we actually get here, people. This is pretty crazy. We get 10, right? And then what's I times I? That's I squared. But remember what I is. I is the square root of -1. So if I square both sides, right, then what do I get? I squared equals -1. So this guy right here is a -1. So look at what my answer actually is. It's -10. So please be careful there. So this way would be wrong because we're not taking into account when we multiply those underneath the radical, it takes away the fact that I'm square rooting a negative and I'm square rooting another negative. We're kind of going around that fact and we can't go around that fact. Let's try another one of those. So another example like that one is, what if I had, the square root of a -49 times the square root of a -36. So again, what you want to do here, square root of -49, that's 7i. Square root of -36 is 6i. And so 7 times 6 is 42, I squared. And what is I squared? It's a -1, so I get -42. Yes, we come out in the real numbers, but please be aware that we have to be careful when we're doing something like that. How do we multiply two complex numbers that are not in the square root form? Well, let me show you. So here's a complex number, 1 plus 3i. Here's another complex number, 2 minus 4i. And I really, really hope that you have like this automatic response to something that looks like this, and it makes you want to FOIL it, which is exactly what we're going to do. So we're going to FOIL this. FOILing really is just distributing each term through to each one, but it has a fancy name, and so we use it because it makes it easy to remember. So I'm going to FOIL. I'm going to do first, I get 2. When I do outside here, I get 1 times a negative 4i. So what you do is you take the 1 times negative 4, that's a negative 4, and then the I just hangs out. That's how we multiply those numbers. We kind of multiply the real parts, and then the I hangs out. 3 times 2 is 6, and then the I just hangs out. Okay, and then last, let's see what happens here. So I have 3 times negative 4, which is a negative 12, right? And then the i's times I, that's I squared. Remember, if we do this correctly, our answer should be able to be written in the form a plus bi. And I want all of your solutions to be written in the form a plus bi when we're dealing with complex numbers. Let's combine some like terms here. So I have 2. This is going to give me plus 2i. And then remember what I squared is. This is a negative 1. So I have negative 1 times negative 12, which will give me a positive 12. So my final answer, notice, is of that form, a plus bi, I have 14 plus 2i. Okay? I hope that makes sense. What if we had something like, oh, wow, that was cool. I have no idea how I did that either. That was awesome, though. Huh. Look at that. What if we had something like negative 1 plus 9i, and I wanted to square this? First off, don't you dare square this and add it together. Don't you dare. That is wrong. You are wrong. What does it mean to square something? I mean, I don't mean to be harsh, but it's like one thing that I hate is when you square over addition. What does it mean to square something? It means to multiply it times itself. So when we multiply it times itself, if you notice, then clearly we're going to be FOILing. So if I FOIL this out, I get a positive 1, then a minus 9i, right? So if you had squared each one, you wouldn't have gotten this middle term. Minus 9i, and then if I do last, I get plus 81i squared. Okay, let's simplify. So I get 1 minus 18i. What is I squared? I squared is negative 1, so I get minus 81. So my final answer is a negative 80 minus 18i. Guys, you would not have gotten that had you squared each one. So please be mindful of that. What does it mean to square something? It means to multiply it times itself, and especially when we're doing that with a complex number, we're going to have to FOIL that sucker. One other one that I wanted to show you, and this one should be pretty easy. I just always forget to do one. We probably should have done one like this before. What if I had a negative 3i times 4 minus 5i? So this is what you would think it would be. I'm going to distribute this. Again, when I find my answer here, my answer should be able to be written in the form a plus bi. That's the goal. So here I'm going to get a negative 12i, right? When I distribute here, I get a negative times a negative is a positive. 5 times 3 is 15, I squared. Okay, what's my final answer then? This is a negative 1. So negative 1 times 15 is a negative 15. I'm going to put the real part first, and I'm going to put the imaginary part second. Okay, I hope that makes sense. You know, there's a lot of, I is an interesting kind of beast here. And I'm just going to state this, and then if you want to go practice some of these, you're welcome to do it. But these kind of drive me a little bit nuts because I don't know why we really care about I raised to huge powers. I haven't really had to worry about that much in my math career, and if someone wants to tell me where we can use it, that'd be great. I cubed. So if you look at some of the powers of I guess it's just kind of an interesting thing to look at. Remember, I is a negative, square root of negative 1. I squared is negative 1. I cubed would be I times negative 1, so it'd be a negative I. And then look at what I to the 4th would be. Well, that'd be I cubed times I, right? Which is negative I times I. which is a negative I squared. But what is what is I squared? It's a negative 1. So something kind of interesting about this number I is that as I take powers of I, my even power is always going to be real numbers, and every fourth power is actually going to just spit out 1. Because now if I multiply by another I, right, I to the fourth times I would just be I. So I guess it's just kind of interesting to see the property of that number. I'm not going to test you really on powers of I. It's kind of fun to do, and it's kind of interesting to see that property of I. And then look at I to the 6th, right, would be I squared, which is negative 1. Anyway, kind of interesting to look at. I just wanted to kind of show you that, and now I'm going to move on because we're going to talk about division. So we've done addition, subtraction, and now let's talk about division. And to do division, we are going to need something called the complex conjugate. And the complex conjugate, I'm sure you've heard of this. Why wouldn't you? So the complex conjugate, or you might hear it just say the conjugate. You've probably used conjugates when you have rationalized denominators of complex radical expressions. But the complex conjugate of a complex number a plus bi, so of a plus bi, is just the same thing except the middle term is changed. Okay, so if the middle term is positive, then the complex conjugate is the middle term negative, and vice versa. Okay, so that's what we mean by a complex conjugate. And the reason, so for example, the complex conjugate of 2 plus 3i would be 2 minus 3i. The complex conjugate of a negative 4 minus 5i would be negative 4 plus 5i, okay? And here's why we care about the complex conjugate. Let's see what happens when we multiply the two complex conjugates together. Okay, let's see what happens. I'm so excited. I can't wait to see what happens. So let's take this first one. If I take 2 plus 3i and I multiply it by 2 minus 3i, okay, I'm going to FOIL this sucker out. So I'm going to get 2 times 2, which is 4. My outside, I'm going to get negative 6i. Okay, inside I get a positive 6i. And if I look at my last, what I get here is a negative 9i squared. Okay, so what ends up happening is those middle terms cancel out. This is what's pretty cool. And I get 4, and remember, I squared, right, is a negative 1. So I get negative 9 times negative 1, which is a positive 9. I was going to put positive 10. And my answer is 13. So look at what this complex conjugate has done. When I multiply two complex conjugates together, the result I get out is a real number. 13 is a real number, right? It's a complex number. More importantly, it's a real number. And I'm going to use this fact to divide. So let me do a couple examples of division and then we'll call it a day. So if I want to divide, let's say, 2 minus 5i, all divided by 1 plus 3i. So remember what I want. I want my answer to be able to be written in the form a plus bi. So anytime I add, subtract, multiply, or divide complex numbers, I want to be able to show that my answer can result in a complex number also. Written like this is not in the form I want. I want a plus bi, and don't you dare break up that fraction just because you want to break up that fraction. So what I need to get is, if I want it in the form a plus bi, what I need to get is I need to get that I by itself. So what I'm going to do is I'm going to multiply by the complex conjugate of the denominator. What that's going to do for me is it's going to give me a real number in the denominator, and then I can divide each term by that real number. So let's see kind of what happens here. I'm going to FOIL the top, okay? So you should be able to do that now. First, outside, inside, and last is plus 15i squared. Okay, and then in the bottom, just like we saw before, I should have, my middle term should cancel. I'm going to do the whole thing for you one more time, and then you should be able to see it from now on. First is 1, outside is a negative 3i, inside is a positive 3i, and then last is a negative 9i squared. And now let's simplify this guy. Okay, so on the top I have 2 minus 11i, 15i squared becomes a negative 15 because I squared is negative 1. Same thing on the bottom. I squared is -1, so this becomes 1 plus 9. And now look at what we got, guys. This is really cool. I get a -13 minus 11i all over 10. And now this next step is important because you need to write your solutions in the form a plus bi. So the way we really explicitly show that that is a plus bi is I divide each term by 10. So what's my final answer? It's -13 minus 11 and then we usually just put the I next to it. The reason we like this form is right away I can see that this is the real part of my number, right? And this is the imaginary part of my number. So you must put your solutions in the form a plus bi, where you break that apart with the 10. I hope that makes sense. What if, if we didn't have, if it looked like we had something that was not a complex conjugate? So for example, if I had 5 minus 8i, and I wanted to divide this all by 3i, you actually could just multiply the top and the bottom by I. That would really work. But if you don't see that, remember this is 0 plus 3i. So what's the complex conjugate of 0 plus 3i? It would be 0 minus 3i. So I'm going to multiply everything by a -3i. Again, you could just multiply by I. That would probably be easier. But if you want to remember, right, that I always multiply by the complex conjugate, then just do it. So I get a -9i squared. We're just going to have a little bit of simplifying to do. We're not scared of that. -15i minus 24, right? I squared is -1, so I get this over 9. Simplify a little bit and rewrite my real part first. -24 ninths minus 15 ninths I, and take a 3 out of all of that. I get a -8 thirds minus, whoops, not plus, minus 5 thirds I. I hope that makes sense. Again, what we could have done, if you want to do this a little bit faster, is I just need to get rid of the I down there. So what if I multiplied the top and bottom by I? Then I would get 5i minus 8i squared all over 3i squared. And if you simplify, you'll see, nope, you won't get that one. You'll get that one. Don't mind that one. So again, how do we divide complex numbers? You want to multiply the top and the bottom by that complex conjugate. Remember, the complex conjugate is just, let's do one more because I can't help myself. What if I had 4i all over a -1 minus 3i? Complex conjugate of that denominator, everything stays the same but that middle sign. So I would have a -1 plus 3i for my complex conjugate. Let's multiply this through, take the 4i through, I get a -4i minus 12i squared. Again, on the bottom, I'm gonna get a +1. My outside and my inside cancel, and then I get a -9i squared on the bottom. Simplify this sucker a little bit, -4i, that becomes +12 because of that I squared. Oh, I keep doing the same ones on the bottom. I'm unoriginal here. So this is 10. So I get 12 over 10 minus 4 over 10i. And then don't leave it like that. You need to reduce your fractions. So 6/5 minus 2/5 I. That is my final answer. That's the complex number. That is these two complex numbers divided. That's always a good time. That was complex. It was unreal. All right, let me know if you have any questions.